Learn like a pro.
Welcome to this explainer. Today, we're going to assemble the fundamental blueprint of how everything moves. I mean, everything. We'll start right from the ground up, constructing the rules that govern motion, from a planet in orbit all the way down to a car on the road.
So, before we start building this engine of ours, let's begin with the question that drove physicists like Isaac Newton. You know, the big one. Are there a set of universal, totally unbreakable rules that dictate how and why things move? Well, the answer, as it turns out, is a resounding yes.
And believe it or not, it all starts with just one single concept: force. Think of it as the ultimate agent of change in the physical world. A single force can completely alter an object's reality in 4 key ways. It can get it moving, stop it dead in its tracks, make it go faster, or change its direction entirely. So let's get to our very first component, right? What exactly is a force? It's the spark, the thing that ignites any and all change in motion.
Okay, in the simplest terms you can imagine, a force is just a push or a pull. That's it. But here's the crucial detail. It's what we call a vector. And that means it's not enough to know how strong the push is. That's its magnitude, measured in newtons. You absolutely have to know which way it's pushing to. That's its direction.
Now, out here in the real world, an object rarely, if ever, experiences just one single force. It's usually being pushed and pulled in a whole bunch of directions at once. So we need a way to figure out their combined effect, their single final outcome. And that's what we call the resultant force, or more commonly, the net force. Think of it like this. It's the final executive decision made by all the forces acting on an object. And it's this single, calculated force that ultimately decides what's going to happen next. Combining forces is actually pretty straightforward. When they all act in the same direction, they team up. They amplify each other. So for example, 2 10-Newton forces pulling the same way just add up to create a much more powerful 20-Newton resultant force. Simple as that.
But when forces act in opposite directions, well, now they're competing. It's a tug of war. If they're perfectly equal like you see on the left, they completely cancel each other out. The resultant force is 0, and we call those balanced forces. But if one is stronger, like on the right, the weaker force gets overpowered, leaving an unbalanced resultant force that points in the direction of the winner. Okay, so let's dive into the first fundamental rule of our blueprint. This one describes what happens in that perfectly balanced state. This is the famous law of inertia. This right here is Newton's first law, and what it's really describing is the default setting for any object in the entire universe. Basically, if you leave something alone, meaning all the forces on it are balanced out, it's just going to keep doing whatever it was already doing, forever. This built-in laziness, this reluctance to change, is what we call inertia. And you can see it perfectly with this classic trick. When you flick the card out from under the coin's inertia keeps it in its state of rest, so it just drops straight down into the glass. The coin literally resists the change. You experience this law all the time. I mean, think about it. When a bus suddenly stops, what does your body do? It lunges forward, right? It's trying to continue moving at the same speed it was before. It's just a fundamental property of matter. It's the reason a satellite, once you get it up into the vacuum of space, can just drift for decades with no engine power at all. It's just following this first law. But what happens when the forces aren't balanced? You know, when there's a clear winner in that tug of war? Well, this brings us to the real engine of our system, the rule that actually creates change in the universe. Newton's second law gives us this beautiful, simple mathematical relationship. Resultant force equals mass times acceleration. You've probably seen it as F equals ma. It helps to think of the force as the driver, the mass as the thing creating resistance, and the acceleration as the final result. This visualizes those key relationships just perfectly. If you apply more force to the same mass, you get more acceleration. Makes sense. But look what happens when you keep the force the same and you start increasing the mass. You get less acceleration. Mass basically acts like a brake or a throttle on how quickly an object can change its velocity.
All right, now for the third law, which adds a really profound layer to our blueprint. It tells us that forces never, ever exist alone. They are always part of a two-way interaction.
So here's the crucial point. Every single interaction is governed by these 4 pillars. Forces always come in pairs. The action and reaction forces are always exactly equal in size. They always act in opposite directions, and this is the one people forget. They always act on 2 different objects. Now, this brings us to a really common trap. So take a look at this diagram of an apple on a book. We see 2 forces, right?
The apple's weight is pulling down, and the normal force from the book is pushing up. They are equal and they are opposite. So, does this illustrate Newton's third law?
The answer is a definite no, and this slide shows us exactly why. The situation on the left, with the apple on the book, is actually all about Newton's first law. Why? Because both of those forces, the weight and the normal force, are acting on one single object, the apple. They're balanced so the apple doesn't move. Newton's third law, on the other hand, is always about an interaction between two different objects. So the apple pushes on the book, and the book pushes back on the apple. That's the action-reaction pair.
Okay, let's add one final, crucial, real-world component to our physics engine. You see, in a perfect theoretical world, an object in motion would just stay in motion forever. But, we don't live in a perfect world. We live in a world with friction.
Friction is a contact force, and it always opposes motion. No exceptions. As you can see in this microscopic view, it comes from the tiny little imperfections on every single surface that catch and interlock with each other, creating that resistance we feel.
And here it is, the complete blueprint. We've put the whole physics engine together. You start by identifying all the forces at play. From there, you calculate the net force. If that net force is zero, the object is in what we call equilibrium. It's either staying put or moving at a constant velocity. But if the net force is anything other than zero, the object accelerates. It's a perfect, predictable, beautiful chain of cause and effect.
So now you have it, the fundamental operating system for the entire physical world. From rockets and roller coasters to robotics and beyond, it all runs on these simple, elegant laws. The only question left is, what are you going to do with it?